All right. So number 15 in chapter 6. What they give you is Br2, CH2, Cl2. That's just a solvent. Just a solvent. Br2 is the reagents on top, solvent on bottom. And they say this is your product. Right? And they say, what's the starting material this come from? So the first thing I would do, you always should do, is number your carbons. So just number these things. 1, 2, 3, 4, 5. So 5 carbons. If you look at this, you should also think, well, this whole chapter has been about alkenes. Maybe the starting material contains an alkene, right? We've been adding stuff to alkenes, right? So if we had to guess, where 2 carbons would the alkene be between? 1 and 2. And now why did you guess that? That's where the functional groups are at, right? You look where the functional groups are at, and that's what makes most sense for the alkene to be, right? Now we've been adding with Br2, you can add 2 bromines, or you could add 1 bromine and then something with the solvent too, right? As we've seen that a lot. What if, right, within the same molecule there was a nucleophile instead of an intermolecular reaction? What if it was an intramolecular reaction? Basically, what I'm saying is these 2 bonds, the O to carbon 2 and the bromine to carbon 1, right, were probably the bonds that we formed, right? We've been adding 2 bonds across alkenes, kind of, right? Whether it's a CH and a bromine, 2 bromines, a bromine, and then a solvent, right? 2 H's, we've added an H and an OH, right? We've done all these things. So I don't think we lost any carbons. And we've said the double bond is between 1 and 2. 1, 2, 3, 4, 5. I'm going to say this alcohol, right, is all within the same molecule. Right, so the way to look at this, right, you've seen if the solvent down here was ethanol, you knew enough to have it attack carbon 2, right? You make a bromonium ion and attack carbon 2, the more substituted one. All the difference here is that the alcohol is all contained within the same molecule. So it's an intramolecular reaction, right? So if we move forward on this, let's just go ahead and let this play out. Oh, I'm going to erase, oh, no I'm not. Pretend it's, okay. Br, let's just do the mechanism. It attacks, electrons go there, comes back down, right? Bromonium ion formation. So let's say 1, 2, 3, 4, 5. We made Br minus. We've also made the bromonium ion, right? So in the first step, we numbered our carbons, right? We identified the electrophile and the nucleophile. The nucleophile was the pi bond, the electrophile was the bromine. Last thing we do is we balance our charge. Overall, in the starting material, we had no net charge. In our products, we should have a minus and a plus, 0 charge, so that balance of charges, good. Now the question is, I mean, in this case, you know, right? You know the oxygen is bound to carbon 2, right? And so now this is a different case. You've seen before where solvent's around, right? And there's so much solvent that it reacts before Br minus can, right? Just because there's so much of it. Br minus is a better nucleophile. It's a better nucleophile than the solvent. It's just there's so much solvent it reacts first. Same deal here. Br minus is a better nucleophile than, right, these lone pairs. But what advantage does that lone pair have on the oxygen versus the Br minus? Well, it has the bonds. Why is this going to react faster than this? Why is this more likely to attack carbon 2 faster than the Br minus is to attack carbon 2? Can you punch yourself in the face faster than somebody else can punch you? Yep. Absolutely. An intramolecular reaction is always going to be faster than an inter, right? This is nucleophile, right? So this is our electrophile. We know carbon 2 is the electrophile. for sure. What's going to happen faster? An intra, where the oxygen's already in the same molecule, or the bromine having to find each other? It's always going to be that intra. So that attacks carbon 2. Takes out. We're not quite done. Nope, I added a carbon. Don't do that. That's why we number our carbons. So a lot of people want to stop here, but we've forgotten something. What should I still have on the oxygen? Hydrogen still should be there. You're in a plus charge. We got to, again, the last thing you ask yourself, did you balance your charges? Alright, so the last step is the nucleophile bromine attacks the H, the electrophile. We get our final product, and there's also HBr in there as well.
So, because we had an ether, you knew that we must have started with an alcohol.
Yeah, so I mean, the trick is starting to recognize these pieces. This is what you're going to start working on next unit. One of the reasons we had you guys make that reaction sheet was so you could start identifying products, right? Because what chemists really do is you show me the drug, the molecule, right? This molecule is going to save the world, and that's the molecule. And then I got to figure out how to make it. So what chemists do is we look at the products and then work our way backwards to see how we can make it. So working on seeing products and then figuring out how to make them, that's the key. That's called retrosynthetic analysis, and that's what we're going to work on more. Right? So it's good to start recognizing these pieces, right? Seeing this carbon 1 and carbon 2 with two things on it and saying, there must have been an alkene or something there, right? And maybe you probably would have saw maybe they're trans to each other. That tells me bromonium ion, right? Besides they gave you that, right? So start to recognize those traits in the products, right? Kind of how we figure out the mechanisms. Remember how we talked about you knew something was a carbocation because, right, it would give you both enantiomers, like a cis and trans, right? Because carbocations are flat. If you don't have any carbocation, right, usually you get either just a trans or a cis product, right? So analyzing the products tells us something about the mechanism, and being able to analyze the products, right, should help us figure out how to make these things. Because at the end of the day, right, what do? We make stuff. So we're practicing making things. So we're looking at exam 3 from 2013 under chapter 6. The first bonus. So I'll go ahead and draw this out. This is your classic, did you number your carbons problem. Alright, so of course we're going to go ahead and number these guys. I'm going to just number kind of the important players here. Cheat a little bit. So ozanalysis, we know, takes an alkene and cuts it, right? Ozanalysis, what it does is it takes an alkene, or cuts it in half, and you end up with 2 new carbonyls. So in this case, I got 2 new formaldehydes, actually here. 2 aldehydes, right? So this is carbon 1, this is carbon 2, this is carbon 1, this is carbon 2 here, right? That's what it does. So if you're given a product of an ozanalysis reaction, basically what you need to do is you need to take the 2 carbonyl pieces and bring them together to form an alkene. So in this case, which 2 carbons would be bonded in the start materials?
2 and 6.
2 and 6. So the easiest way to draw this, just do that first. All right, and say, okay, 2 and 6. You could also count here and say 1, 2, 3, 4, 5 emerald ring, and just kind of build it from there. I want to use it black. All right, doesn't need to be pretty. Carbon 6 is bonded to 2 things. One of those things was this phenyl ring off here. Carbon 6 is also bonded to carbon 5. So that must be carbon 5. Carbon 5 was bonded to carbon 4. What else was carbon 4 bonded to? that methyl.
Oh, okay.
Carbon 3 is bonded to carbon 4, and carbon 3 is also bonded to this isopropyl. Carbon 2 is also bonded to carbon 1, which is right there. Right, so that's how I piece it all together, working backwards. Okay, so the term optically active, that refers to rotation of plane polarized light. So what does that? What rotates plane polarized light? Chiral molecules do, right? So chiral molecules are optically active. Right? Generally speaking, that means things with asymmetric centers, but not always, right? So usually it means molecules, right? It means molecules with asymmetric centers. Yikes. Centers. Right? The one exception of that, of course, is mesocompounds, right? Which are achiral even though they have asymmetric centers. So most molecules with asymmetric centers are chiral, except for mesocompounds, which have those internal mirror planes. Right? So even though a mesocompound might have asymmetric centers, it's not optically active because mesocompounds are achiral. So it's not always at asymmetric centers. Usually if you have asymmetric centers, you're chiral and you rotate plane polarized light, but not always. All right, let's go old school. See if we can still do R and S. First thing we gotta make sure we identify, right, is there an asymmetric center? Asymmetric center is defined as an sp3 hybridized atom with 4 different things bonded to it. So right, this carbon is sp3 hybridized and indeed has 4 different things. The next step is to rank them, right? And don't forget our red, white, and blue priorities, right? Red being number 1, blue number 2, blue, red, white, white number 2, blue number 3, and then green is the last. Right? You always have your 2 enantiomers, your 2 molecules with you. Don't forget your molecules. So here, usually it's easiest to rank the top 2. So the top one, I'm going to go with the OH is red, the H is green. Now we got to rank the other ones. So to do that, right, we go carbon to carbon, tied. Best play this carbon has is an H. Best play this carbon has is another carbon. Winner. So we'll call this one white, and then this one has to be blue. All right, so now at this point, you take one of your 2 molecules and you map it onto this molecule. And only one of your molecules should fit. Once you figure out which one fits, you grab the green ball, you turn it towards yourself, and see which way it rotates, red, white, and blue. Clockwise or counterclockwise? Clockwise R, counterclockwise S. Yep, I'll do one of those too. So let's say, okay, so this one ends up being S. Hopefully that made sense to you. So another way we could ask one of these questions, let's say we made a molecule, I'm just going to make one. So we made that and said, we want you to make this asymmetric center, we want you to make it R. Add in the wedges and hatches. Right? Still, the first thing you need to do, of course, is what? You need to rank them. Still got to rank them. Right? Still rank them. So I would rank them, let's see. Lowest one is going to be H, that's green. Then the highest atomic number one is bromine, so that's red. Fluorine's next because it beats carbon, so that's white and blue. So we rank them, good. And now at this point, right, you need to do what? You have two molecules in front of you. One's R and one's S. Which one should you grab?
Oh, so
The
you
R,
want it to-
right? Grab the R1. Grab that R1. Grab that R1, right? And essentially at this point, you can put the wedges and hatches wherever you want, as long as the wedges and hatches are right next to each other. Right? The wedges and hatches must be next to each other. Right? So you can make blue and white wedged and hatched. You can make white and red wedged and hatched. Right? But they have to be next to each other. You can't have them across. So
What's the reason for that?
if you have them across, it's not defined. It's not clear, right? The wedges and hatches need to be right next to each other, right? So there's lots of different answers for this one, right? Does anybody have one they want me to do? We have a green wedged, R hatched, right? That's the R version of this. Yes, it is. Good. I could have done the wedges and hatches on different sides, right? I could have easily made this thing S before too, but it's just a matter of picking right the molecule and mapping it on there. All right, let's do a Fisher projection. H, ethyl, isopropyl, terbutyl. All right. Step one again. Let's rank them. So the lowest ranked one is green. The highest ranked one is red, white, blue. Just refresh ourselves. I can do that kind of fast now. Green, we should all know, just because hydrogen is always going to be the lowest. Red, white, and blue, they all have carbons, so it's a tie. Best play here is a carbon, best play here is a carbon, best play here is a carbon, still tied. Best play H, best play carbon, winner, best play carbon, winner. So this is the third, hence blue. These two versus each other, carbon to carbon, tied. Finally, this guy's playing H. This guy sells another carbon to play, winner. Right? So red, white, blue, green. Now, what does it really look like? Right? Is that these are wedged. The things horizontal are wedged, and the things vertical are hatched. Again, now at this point, you take your model, one of your two models. One of your two models will have to fit this. Once you figure out which model fits this, you grab the green ball, you turn it towards yourself, you say red, white, and blue, and whichever way that rotates, clockwise R, counterclockwise S. So be careful when you're doing these, right? Make sure it really matches up, right? Green and red had to be going away from you. White and blue had to be coming at you. So this one ended up being R. Good. Okay, so I have pre-drawn a couple molecules. So let's look at these two first. These are just kind of templates we'll use in a second. So let's try to figure out the relationship between molecule A here and molecule B. Right, we're comparing two molecules to each other. So what are some possibilities? They could be constitutional isomers, meaning they have a different bonding pattern, a different constitution. They could be identical. They could be diastereomers. They could be enantiomers. Right? Those are some possibilities they could be. So what are these two molecules to each other? As we're looking at this, there's four possibilities. Constitutional isomers, but it looks like they have all the same bonds, right? If we numbered our carbons, why not? 2, 3, 4, 5. 1, 2, 3, 4, 5. I know there's another carbon. I know there's a carbon up there, but carbon 2 has all the same bonds as carbon 2 in both molecules. So does 3 and so does 4. Right? Different spatial arrangements, so they're not constitutional isomers, they're stereoisomers of each other. So they're not identical either, right? So we've narrowed it down. They're not constitutional isomers. They're not identical. So they either have to be enantiomers or diastereomers. If they're enantiomers, every one of these, right, there's 1, 2, 3 stereocenters. Every one of these, oops, is there 3 stereocenters? Now there is. Whoops. Sometimes, right? There was two methyls there. That wasn't a stereocenter. Now it is. Now it is. Okay. Okay.
Okay.
Okay. So if they're enantiomers, every stereocenter has to be flipped. So not one could be the same. So which is there a stereocenter that's exactly the same in A and B?
Yes.
Yes, there is. What at which carbon? Carbon 2 appears to be exactly the same, right? So if that one stereocenter is the same, and at least one other is different, what do we have here? We have diastereomers. So A and B are diastereomers. Diastereomers.
Could you call these geometric isomers?
No, geometric isomers refers to E and Z.
Only easy?
Only E and Z. Yes. So A and B here are diastereomers. Let's try this. Could you take A, let's take molecule C. I want A and C here to be enantiomers. Could you do that? Can you take A up here and draw on it here so it's all enantiomers? What would I have to do? I might have to change something.
Wouldn't you have to switch them up?
How could we do it? You might have to erase if it was possible. It's not possible. That methyl can't be here anymore, can it? That methyl needs to be there. I'll get you started. Heck, I'll get you started. There's an OH there. Right? So I flipped carbon 2. So let's number our carbons. 1, 2, 3, 4, 5. Let's see if you can fill in the 3 and 4 to get the enantiomer of A. Right? So what do we have? So essentially what we need to do is just flip around these guys. So the Cl is coming out, H is going back. In our enantiomer, we'd want the H coming out, the Cl going back. On 4, H coming out, F going back. That gets us to our enantiomers. Nice. How about for this one over here, of course, darn it. Let's draw for D. Let's make D and B. Let's draw diastereomers of those two. So let's turn D into a diastereomer of B. So let's take D here and make it a diastereomer of B. So one way to do that, I'm just going to leave this the same. I'll number the carbons for you. 1, 2, 3, 4, 5. So make D a diastereomer of B, but don't make it A. Make D a diastereomer of B, but it can't be just like A. We're back. So if we want to make D a diastereomer of B and not be A, how do we do that? There's only one way, I think. The which one? I can't flip.
Just make the Cl.
I have to leave one of them the same. So I already have carbon 2 is the same. I have to have at least one different than B. So it doesn't matter which one I pick. I just got to pick one. So let's say you said, let's make fluorine coming out, and this is H. Right? So that's different than B. But then I got to make 3 needs to be different than A. So it has to be H and Cl. Make sense? So here's an interesting one, right? Between B and D, they're still diastereomers. How many stereocenters, how many asymmetric centers do they have in common? So each of them has 3, but how many of them are exactly the same? For between B and D, how many asymmetric centers are the same between B and D? 2. Both carbon 2 the same and 3, but one's different, right? All you need is one the same and at least one different. So these are still diastereomers. it's not like if you have two different, you're more of a diastereomer. You're still, all you need is one the same and at least one different. So these are still diastereomers, even though they share two stereocenters. But one's different. That's all that matters. One the same, at least one the same, and at least one different, you're diastereomers. So then let's cherry on the top of this. C and D to each other are what? C and D are diastereomers to each other. What about C and B? What are they to each other? They're also diastereomers. And they're all freaking diastereomers. Except for, of course, A and C, which are enantiomers. Last question. Here we go. Conformational isomers. All right, chlorine and fluorine. All right, 6-membered ring. It can be a chair conformation. You can draw chairs two ways. Number your carbons. If something's pointing up, it'll always be up. In a chair, though, you can either be axial or equatorial. Axial or equatorial has nothing to do with being up or down. You can be axial and be up. You can be equatorial and be up. But in this case, the chlorine's always going to be up. And it's on carbon 1. So if I draw the first thing in, this is axial up. Fluorine is on the opposite side of the ring, pointed down. So on carbon 1, it's equatorial down. Now when I do this ring flip, this is carbon 1, 2, 3, 4, 5, 6. Right? Essentially what happens is carbon 1 gets pulled down, carbon 4 gets pulled up. So this is still carbon 1. Chlorine's still on carbon 1. Is chlorine still pointed up? Yes, absolutely. It has to be, right? It's always up. But is it in the axial position now? On this ring, is it axial anymore? No. Now it's equatorial. So now it's equatorial up, and fluorine is axial down. So what these two things are to each other, these are conformational isomers. Right? Same bonds, right? They're just different conformers of these things. Right? They rapidly interconvert into these things. Right? The chlorine is always up, so it's not changing its It's not changing its three-dimensional space. It's still always up. It's just in a different conformation.
So because the chlorine was the wedge, then it was up.
Yeah, because it was wedged, I said it was up. Yes.
What if you said, oh, it's wedge? Did you said it was down?
Yes.